On today's episode, Dude, Where's My Spaceplane? Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. Remember Stanley Kubrick's brilliant 2001 A Space Odyssey? Now in that film, passengers flew a Pan Am spaceplane to a gigantic orbiting space station, an idea not very far-fetched from the perspective of the late 1960s. Now while that space station did indeed happen, the hypersonic orbital airliners are dead on arrival. But why? Now, I pondered this question the other day when I came across a mention of the reaction engines company SABRE engine concept, a very novel propulsion system that promises to work well in both low altitude and low speed flight regimes, as well as at hypersonic speeds, potentially up to orbital velocity. Now, if it could be made to work, it could be a game changer. The technology is complex, but the key is the use of a novel intake air pre-cooler that dramatically lowers intake air temperature. So why refrigerate the intake air? Well, heat has been the perpetual problem of all very high-speed aircraft and jet engine design since the very first turbojets in the 1940s. Now originally the problem was the materials in the jet engine hot section turbines, but by the 1950s airframe heating became not just a problem but an absolute speed limiter for very high-performance aircraft. Now to get to suborbital and orbital spaceplanes, not only will the airframe get extremely hot, but so will the engines. Supersonic combustion ramjets or scramjets are currently the hot ticket to hypersonic flight in military applications like air-to-surface missiles. But the dirty secret to their performance is that they can operate successfully over a life expectancy of only 3 or 4 minutes, with the missile impacting before the engine melts itself into liquid. For true hypersonic flight in the region of Mach 5 or so, in a reusable and commercially viable airplane, managing the heat rise caused by both frictional heating and the very high compression of the intake air charge is what hypersonic technology is going to depend on. And the SABRE engine does this using a gaseous helium coolant loop, chilling intake air from 1,000 degrees C down to minus 150 degrees C in 0.01 seconds. Now that helium coolant loop is the secret sauce of this design, capturing the absorbed heat and using it to drive pumps and compressors for both the engine's liquid hydrogen fuel and for the cooling system itself. Just preventing the ambient water vapor from icing the engine is something of a miracle, but for a commercial application, the technology is going to have to combine some of the features of a turbojet, a ramjet, and a rocket engine. Now conceptually, the most difficult part of the program is the pre-cooler, and it's been tested successfully, but the system is going to be very complex and expensive. So will it produce a hypersonic ticket that you or I can buy a ticket on? Eventually, yes, but market forces aside, it's worthwhile to remember that a century ago, commercial aviation only existed because of government subsidies. In the US, airmail service was paying the overheads for early airlines until the airplanes became big enough to carry an economically viable number of passengers. Now, if similar scaling factors apply with hypersonics, it's going to require huge airplanes and be a lot more difficult than just adding horsepower to piston engines. Now, I hope it happens before I die, but I wouldn't bet the farm on it. Well, that's it for today's episode of End of the Line, brought to you by Engineering.com. For our deeper engineering series, visit Engineering.com TV for exclusive shows like Manufacturing the Future, Designing the Future, and the Engineering Roundtable, not found on our YouTube channel. The links are in the description below. Thanks for watching.